Hi, welcome back. We are on to cardiovascular physiology topic focusing on capillary exchange. So that's key part of your circulatory system where things are actually happening. It's not just blood moving through tubes, but we're actually going to get some communication between the circulatory system and your tissues, your peripheral tissues, and all the goodies that need to be dropped off and all the waste products that have to be picked up. So in your notes, there's a listing of 4 things that are important in capillary exchange. So I'm just going to read through those to make sure I hit them and not overlook them. So first is it ensures the plasma and interstitial fluids are in constant communication. So we don't have stagnant collections of fluid in any one place. So what's going on in your blood will affect what's happening in your interstitial fluid, and what's happening in your interstitial fluid will be picked up by your blood plasma. So we're in constant communication between those 2 compartments of fluid, your blood and your interstitial fluid. Number 2, accelerates distribution of nutrients, hormones, dissolved gases throughout the tissues. So the exchange is where those things happen. So clearly we're going to accelerate that when we actually have it happen. Number 3, assists in transport of insoluble lipids and tissue proteins that cannot enter the bloodstream by crossing the capillary walls. So this exchange allows for the transfer of these insoluble lipids and proteins, these larger structures, most likely through the fenestrated capillaries and the sinusoids. And then lastly, your blood supply or your exchange that's happening in the capillaries can have a flushing action that carries bacterial toxins and other chemical stimuli to your lymphoid tissues. Think spleen, tonsils, lymph nodes, to be handled there. So again, we don't want a stagnant area where bacteria and toxins can build up. We want to flush that into the blood supply, because then that's going to go and signal your immune system to start its attack or to try to fix the problem, which we're going to be seeing the first thing when we get back from spring break is our lymphatic system, one of my favorites body systems. All right, so now that we've kind of set up, those are the reasons or the benefits of having capillary exchange, because if we don't, we die. I should add that on my own, is we need to take a look at how things can transfer across from one compartment to the next. So enjoy my PowerPoint art and animations here. So this is my picture of a capillary, a fenestrated capillary, because there is a pore. So this is my capillary. My pink and my yellow cells are my endothelial simple squamous epithelium. And just to remind you, this diagram is going to be taking a look at diffusion. So things move from an area of high concentration to low concentration. So that should be kind of ingrained in your science brain from general bio, high to low. That's passive transport. We don't need to burn any energy to do that, and that's just the tendency that things like to do. So within a capillary, where are some of the places that this diffusion can happen? So there's 5 things listed here. I'm going to illustrate a few of those. So one is if you are in a fenestrated capillary or maybe even a sinusoid, you can diffuse directly through the pores. Well, this is specifically for fenestrated capillaries. You can diffuse, again, high to low through the pores. Second, if you are a water-soluble polar substance or large in size, you have to rely on the membrane channels. Think glucose channels or amino acid channels, ion channels, things that have to do facilitated diffusion, basically facilitated diffusion. The next path is between adjacent cells. So this might be more common in sinusoids where you have the gaps. You don't have tight junctions, you have gaps that larger things can move through, those adjacent cells. And then the last one that I have illustrated here is through just simple diffusion. This is going to be your lipid-soluble, hydrophobic, non-polar substances that can diffuse directly through the phospholipid bilayer of the endothelial cells. Okay? And then sinusoids are kind of more like the adjacent cells, or those big gaps that you might see. Okay. The other force, if you will, that can move things across the capillary is filtration. So what we just got done looking at was diffusion, which is concentration gradients, high to low concentration. Filtration is based on pressure. It's the same idea though. Things like to go from high pressure to low pressure. And we're talking about that hydrostatic pressure. So going back to when we were talking about arterial pressure, venous pressure, capillary pressure, those were all hydrostatic pressures. We are going to be focusing on the blood pressure in the capillary, which we call capillary hydrostatic pressure, CHP. Okay, so if you have a higher pressure inside of the capillary, things are going to leave to the lower pressure in the interstitial fluid. If it's the other way around, if the pressure in the capillary is lower, then stuff will move from the interstitial fluid into the capillary. So it just follows the same high to low principles based on pressures though, not concentration gradients. So this is showing you that you can get some filtration through the pores, you can get filtration through the adjacent cells, like this kind of diagram here on the bottom. And these are going to be some things that can fit through those spaces. Your large blood proteins and glucose, maybe, maybe not. It's all size based on this pressure filtration idea. Okay. So now we're going to take a look at some of the pressures. We have already identified capillary hydrostatic pressure. The next thing we're going to take a look at is something that we call BCOP, or blood colloid osmotic pressure. So again, my beautiful PowerPoint art here illustrating this idea of blood colloid osmotic pressure. So osmotic pressure, if you remember, osmosis, water moves towards higher solute concentrations. Again, just like diffusion, things like to go from high to low. Osmosis goes from high water to low water. But the other way you can see that is water goes towards a higher solute concentration, because if you have high solutes, you have low water. So in our blood vessels, we have big red blood cells. They're too big to leave the capillary, obviously, so they stay inside. And then I also have created these little cloud-like things, which are mainly albumins. Those were the highest proportion of our plasma proteins, if you think back to chapter 19, and other large plasma proteins, just the collection of these things that stay in the plasma. They're too big to filter out or diffuse out, so they just always are staying in your blood vessel, in your capillary. So when we have this higher, so this is going to be hypertonic, if you will, to a hypotonic external environment. So just like we learned way back when we were learning about isotonic and hypo, water moves towards hypertonic situations. So that's these orange arrows are saying, okay, so if we have all of these things inside the capillary, there is a tendency for water and other dissolved substances to be drawn back into the capillary based on this osmotic pressure. That's what we call blood colloid, because colloid is representing all of these large kind of suspended proteins. Osmotic, water goes towards higher solute concentrations, pressure. So BCOP is a tendency pressure to go back into the capillary, where hydrostatic pressure tends to push stuff out. So now what we're going to do is combine the relationships between the outward forcing capillary hydrostatic pressure via filtration and the inward drawing force of BCOP for reabsorption, and take a look at how all of that comes together to do capillary exchange. All right, this is a big picture. So if you remember, when we were taking a look at that graph of just systemic blood pressure, it kind of went down like this, right? And the capillaries are right here in the middle. They went from 35 to 18. Those are the numbers that are really important for us right now in this capillary. So from the beginning of the capillary to the end of the capillary, what we call the arterial end, through the capillary to the venual end, we are going to have a change in capillary hydrostatic pressure from 35 millimeters of mercury to 18. Okay, so that's our capillary hydrostatic pressure. That blood, right, so this is this guy here. The blood colloid osmotic pressure doesn't change. And the reason why it doesn't change is because the number of red blood cells don't change. The number of albumins don't change. The number of those large unfilterable proteins in the plasma don't change. So our they're just calling it, they got rid of the C, I guess. I learned at BCOP. So this doesn't change. It's always 25. So this blood colloid osmotic pressure, stays 25 the whole way. Okay, so we're going to see that in some of these math equations. We're just finding the difference. So let's say at the arterial end of your capillary bed, you have 35 millimeters of mercury. So that's pushing out. This is a filtration outward force. Okay. But then you have to take into consideration there is an inward force. This is the blood colloid osmotic pressure force that's trying to come in because of the osmotic draw of those albumins inside of the capillary of about 25 millimeters of mercury. So this is an inward force. So if we find the difference at the arterial end of the capillary, we have a net out of about 10 millimeters of mercury. So at the beginning of your capillary bed, this is where we see primarily filtration, right? Oops, I kind of drew over the number. So here's our filtration. We're just finding the difference between capillary hydrostatic pressure and blood colloid osmotic pressure, and we have a net filtration pressure of 10. Can't draw squares today. All right, so that's where that 10 comes from, is the subtraction of the inward force from the outward force, and we have 10 more units of outward force, so we're going to get filtration. Now, if we cruise down our capillary, right, so 35, 30, 25, 20, 18. So our capillary hydrostatic pressure is decreasing. Somewhere around the middle, we are going to have, I'll just erase this part and just put in the new numbers. So somewhere you're going to have a 25 pressure outward force minus that unchanging BCOP inward force, and we're going to get a zero net movement. So net filtration pressure of 0, where the capillary hydrostatic pressure is equal to the blood colloid osmotic pressure. So we don't get any net gain or loss. Stuff is still moving. Stuff is going out, stuff is coming in, but at this middle part, they're equal. Okay, now we're moving down the line, and our capillary hydrostatic pressure is getting lower. Okay, I can actually leave the BCOP because it doesn't change. So now at the venule end, kind of towards the venule end of our capillary, the out pressure is now 18, but that BCOP is staying the same as in, right? So now we have a negative out pressure. Well, that doesn't make any sense. But if you're going to take it as the net gain or loss, we have a net filtration pressure out of -7, which you can reverse that and say, okay, so if it's a negative out, that means it's a positive inward force. And so this is where we see reabsorption. Okay. So this is the main factors of this exchange process that's happening along the capillary bed. We have a net filtration out on the arterial side of the capillary and a net reabsorption in on the venule side of the capillary. But again, please know we are going out every, I'll do purple. We have stuff moving out along the entire capillary bed. And we have stuff moving in along the entire capillary bed. So it's not like we're just shoving a whole bunch of stuff out at the beginning and sucking in a whole bunch of stuff at the end. It's a constant flow. We just have more stuff being moved out on the arterial end and more stuff moving into the capillary at the venule end. So it's this net change that we have to focus on. So this is what's happening in every single capillary in your entire body every second of every day. So this is our capillary exchange. Now, if we take a look at that difference, we had 10 units out at the arterial end and -7 moving in on the venule end. Those aren't the same. So we have more out than we do in. So there's a difference of about a little bit less than 4 liters a day of excess fluid. So we don't reabsorb the same volume that gets filtered out at the arterial end. So where does it go? We don't just blow up into these big squishy, interstitial fluid blobs. we have our entire lymphatic system to take care of that. And that's what we're going to be talking about when we get back from spring break. Again, our first chapter when we come back is the lymphatic system. We're going to talk in more detail about where that excess fluid goes. It actually becomes lymph, part of your lymph circulation. So we have a way to take care of that, which is a great thing. It's not just extra, it serves a whole other purpose, which is going to be chapter 23 stuff after spring break. So this is our interplay between filtration and reabsorption. This allows nutrients, oxygen, hormones, ions, other signaling molecules to be dropped off at the capillary bed, carbon dioxide, waste products, hormones, proteins, amino acids, things that need to get back into circulation can get back into circulation. So that constant communication between interstitial fluid and capillary bed, this is that big picture. So this is super duper valuable. Okay, that wraps up our physiology of exchange of the capillary bed. I will see you next time. Bye.